Okay, so in this lecture, let's discuss yung harmonic response of a single degree of freedom system. Pero this is undamped. No? If you notice, no damping dun sa equation of motion. Okay, so previously, this is zero, no? Because free vibration. Since we have now a harmonic response in the form of P naught sine omega bar t, so the equation of motion is now mu double dot plus ku equals P naught sine omega bar t. Omega bar, that means yan yung excitation frequency nung force. Okay, now this is again still a linear second degree linear differential equation, but non-homogeneous because hindi ka na naka-equal sa zero. So in this kind of differential equation, if you review back your differential equation, okay, so we have the solution of the particular solution and the complementary solution. If this is the case, no? So let's solve first the complementary solution such that i-equate natin yung equation of motion na homogeneous siya. So similar dun sa previous video natin. So still mu double dot plus ku equals 0. Meron akong subscript na h, that means homogeneous part to ng differential equation. So again, that the solution as we previously did is this one, C1 sine omega t plus C2 cosine omega t. So, alam na natin to. We did this already sa previous video. I-plug in na lang natin yung solution mamaya. Now, what we do not do yet, no, is the particular solution. Okay? So, I have now a subscript of P. So, mu double dot P plus ku P sub P equals P naught sine omega bar T. Okay, if you notice also, kaya may bar nga yung omega dito, that is yung frequency ng load. No? Etong omega na to here sa above, yan naman yung frequency ng structure mo. The natural frequency of your structure. Okay, so para ma-differentiate. Okay, so let's continue again. So similar solution. Our solution is in the form of G1 sine omega bar t plus G2 cosine omega bar t. So binago lang natin yung variable, no? Instead the C1 C2, it's now G1 G2. Okay. So get the first derivative because binago because it's now we're now finding the particular solution. U dot P sub P is equal to G1 omega bar cosine omega bar T. So that's the first derivative of sine omega bar T minus G2 omega bar sine omega bar T. So first derivative of G2 cosine omega bar T. And the second derivative is this one. Okay. Naging omega bar square na because if you differentiate cosine omega bar T, that is sine omega bar T times omega bar, diba? So omega bar square na siya. Okay. And so we now have the u double dot or the second derivative. Now plug in natin to. Gamitin ko lang yung zoom in. So let's plug this dun sa ating equation. Okay? So ito na siya. Okay? And then plug in naman natin ito u sub p dito. Okay. Dito pala dapat yan. Yan. And this one is yan. So plug in mo lang yan. You can have this. Okay. And find the common factor. So, in-extract ko na siya. So, G1 omega bar square ito, G1 omega bar square sine omega bar t, and then G2 omega bar square cosine omega bar t. So, yan. So, familiar na kayo dyan. Because, minultiply natin to sa M, di ba? Sa mass. Okay. While, for K, minultiply naman natin yung K sa UP, U sub P. So, that is G1 sine omega bar t plus G2 cosine omega bar t. Okay. And then, extract natin si G1 sine omega bar t. Yan. So, if you notice, di ba, meron kayong common factor na G1 sine omega bar t. So, this is G1 sine omega bar t. And also, we have G2 cosine omega bar t, G2 cosine omega bar t, G2 cosine omega bar t. Okay? And anong naiwan? So, if we extracted G1 sine omega bar t here, you will be left with K minus omega bar square M. This one yun. Tama? Okay? So, ganun din dito. K minus omega bar square M. Okay? And then, everything equal kay P naught sine omega bar t. Okay. Now, this is important. No? If you have this kind of equation, no, that means, no, we have, if you notice, you have, on the left-hand side of the equation, you have sine omega bar t and cosine omega bar t. On the right-hand side of the equation, you have a term sine omega bar t. Yan, no? So, if this is the situation, that means, no, this one, this part, na may sine omega bar t is equal to this part, the right-hand side of the equation. Okay? So, if that's the case, therefore, itong term na to will now be equal to 0. Yan. Okay? So, ito natin. Yan. So, therefore, K minus omega bar square M is equal to P naught sine omega bar t. Okay? Now, since you have common term sine omega bar t, makakancel out yan. What's left is this one. K minus omega bar square M, G1 is equal to P naught. While itong term na ito, no, everything here will be 0. Itong term na yan. So, this is 1. Okay? So, that means G2 is equal to 0 because of this. Okay? So, we can now find G1. So, G1 here, transpose natin, is equal to P naught over K minus omega bar square M. Okay? So, we now have G1 and G2. Yan. We can now plug in yan sa ating original equation ulit. G1 and G2. Okay, so UP is this one, right? U sub P. And we know G2 is equal to 0, so this one is 0. Therefore, what's left is this one, G1 sine omega bar t. So, plug in mo to, G1 sine omega bar t. So, that is your particular solution. U sub P is equal to P naught over K, 1 minus omega bar over omega, all over square, times sine omega bar t. This happens because, remember, omega is equal to square root of K over M. So, inano lang yan. We just did a simplification. So, naging ganito na yung equation natin. Okay? What do you notice? So, what we have here is P naught over K. Remember, dun sa first video, and as I explained, what is the general formula of stiffness method? P equals K U. Right? So, therefore, U is equal to P over K. or P naught over K. What does it mean? So this is a static, static deflection. Yeah, that means if you know the static deflection of your structure, imumultiply mo lang siya sa term na to get the dynamic deflection. Yan, okay? So that's the physical meaning of this equation. So that's why you still need to do static static methods, no? And then if you know the frequency of the excitation, the omega bar, and then the frequency of the natural frequency of your structure, and multiply mo lang yan, then you will get the dynamic deflection. Pero I'll explain this further here. So kasi particular solution pa lang yon, no? So the total solution of the differential equation is the combination of the homogeneous solution, complementary solution, and the particular solution. And we know na ito yung solution ng homogeneous solution natin earlier, and we will add now the particular solution, which is what we get. Yeah. Okay? But then plug in nyo yung equate nyo na u at time 0, no? At time 0. So if I plug in here cosine okay, so using our initial condition na u naught, your u at time 0 is equal to 0, so I'll plug in here. Okay, so u at time equals 0, so C1 sine 0 because our t is 0, C2 cosine omega 0. Okay, so every cosine 0 is definitely 1. So yun. And ito, our u sub p is equal to p naught all over k. And since we have here sine times 0 is simply 0. So all the terms here are 0. That leaves our C2 equal to 0. Kasi our u naught or u at time 0 is equal to 0. Okay? So therefore, mawawala yung term na to. Yung C2 cosine omega t. So what's left will be u of t is equal to C1 sine omega t plus yun nga, the particular solution. Take note, beta is the frequency ratio, omega bar over omega. Okay? And if omega bar or the excitation frequency ng load is equal to the natural frequency of the structure, no, you get the resonance. No? So na-amplify further yung yung displacement mo if you have resonance. Okay? Okay, so let's now find C1. So find the first derivative. U dot is equal to C1 omega cosine omega t plus P naught over K 1 minus beta squared kasi nga omega bar over omega is beta sine omega bar t. Derivative niyan is omega bar cosine omega bar t. Okay, then C1 equate everything to 0 because our initial velocity is 0, u dot. So C1 omega plus P naught over K, okay, is equal to 0. Therefore, our C1 is equal to negative P naught over K, 1 minus beta square omega bar over omega. Or C1 is equal to negative beta P naught over K, 1 minus beta square. So we now have C1. Plug in natin yan dun sa ating solution. And we have this. So U sa function of time is equal to P naught over K, 1 minus beta square sine omega bar t minus beta sine omega t. As you notice, there's no damping term here. No exponential decay because it's an undamped force vibration. Okay. So the graph of this equation is, I'll show you here, is this one. Yeah. So if you notice, you have two response, the steady state response and the transient response. So, and the blue one is the total response. So, and this is, since this is undamped, so infinite yan. Infinite tong curve na, itong graph na to. So, the steady state response is itong portion na to. Where's that? This one. Yeah, that's the steady state response. Okay. This one. So, that is the steady state response. Okay, so, and since we will add that with the transient response, ito, this one here, this one, transient response, this one. So the total response will be this, the blue. Okay. Okay, but let's now, if you go further to a more realistic situation, like a damped structure, you know. So in our case, for structural engineers, our structures have an inherent damping. The solution is quite mahaba, no? Quite long. I'll just show you the final equation. So this is your final this is your solution, no? To damp, I write down damped force vibration. So damped force vibration. Okay. So if you notice, dahil we now have the damping, we also encounter again the exponent. That means exponential yung decay, no? Yung decrease, pag-decrease nung iyong response. If your damping is greater than 0. Damping ratio. Okay, so this is familiar, no? You are familiar with this. P naught over K, no? Encounter nyo ulit to, no? And this is the steady state response, no? Or in mathematically, in your differential equation, that is your particular solution. Okay? And if you combine this, it is this whole equation. If you plot this in Excel or in a graph, you will get this. If you notice, the transient response will die out. And matitira na lang yung steady state response. Okay? Okay, kasi may damping. No? Because you have damping. And therefore, what's important in a typical structure or building is the steady state response. Itong term na to. Because siya yung matitira. Okay? Yan. Now, so extract natin yan. Yung steady state response na solution na yan. This one. P naught over K minus beta square plus 2 zeta beta square, square root sine omega bar t minus theta. We just transform this steady state response solution into this, but they are the same. Now, wherein theta is equal to arctangent 2 c beta minus 1 beta square. And again, let's simplify that further. Our U is equal to d P naught over K sine omega bar t minus theta. So this is what I'm saying before, that if you do the static analysis, therefore your U is P naught over K. Diba? Ito yun. And simply multiply mo lang siya sa D. That is your dynamic amplification factor. Then you will get the maximum response of your structure. And the dynamic amplification factor is simply this one. Okay, this one. Yeah. And if you notice, your dynamic amplification factor is a function of the excitation frequency ratio, diba? The ratio of the excitation and the natural frequency of your structure. And of course, the damping ratio of your structure. which is typically in a building, it's about 5% or 0.05. So if you know the frequency ratio of your loading and the damping ratio of your structure, you will get the dynamic amplification factor. And if you know the static deflection, just multiply that with this, you will get the maximum response. Okay?